Okay, so the third lecture we will discuss in this lecture is correlation and model specification, but as usual I would like to very quickly remind you of what we discussed last week. So what we discussed last week, we looked at the OLS from the first week, and we now understand that in the OLS estimation we try to minimize the sum of the error square. This equation, so we try to minimize this term, and these are the assumptions that we make in the classical linear regression model. So we assume that the model is linear in parameters. We discussed this last week. We assume that the regressors are fixed, non-stochastic. The expected value of the error term is 0. We assume we have homoscedastic errors. We discussed this last week. And what we will look at today is this assumption, no autocorrelation and no specification bias. But before we start with the new topic, so again from last week we discussed the issue of linearity in OLS. We made this distinction between linear in variables and linear in parameters, and as we discussed last week, so we could have a model that is not linear in variables but still linear in parameters. This could be estimated by OLS, while this is an example of a model that we cannot estimate using OLS. Again, this is another example. This is one of the examples we looked at last week. We looked at the models, some models that are not linear in variables but still linear in parameters. One of the very famous model here is the Cobb-Douglas production function, and we said this could be transformed into a linear in parameters. So this is a model that is linear in parameter, but it's not linear in variables. This is in the log form, and we can estimate this easily using OLS. The second example we looked at is the log-lin models, where the dependent variable is expressed in the log form, and this is the growth model, and we explain how to interpret beta and beta2 in this sort of models. The third types of models we looked at, the inverse model, which is this is the general form, and we explained how when x goes to infinity, this term become very close to 0, and the y here, or the dependent variable, approach the constant or beta1, and we explained this too as well. So this is all from last week. We also looked at multicollinearity, what it means, the implication of having multicollinearity, and we explained that OLS estimators are still blue, best linear unbiased estimators, but sometimes you will have, with the presence of multicollinearity, you would have high R squared, but you will have insignificant coefficients, and that is the main problem. How to detect from multicollinearity, this is something we discussed as well. So you could have calculate the high pairwise correlation among the explanatory variables, or you could run an auxiliary regression, or you could look at the variance inflation factor. These are things that we already discussed last week. We also discussed last week heteroscedasticity. We explained what it means and what are the implications for OLS in the presence of if heteroscedasticity exists. We explained that the estimators are not blue because they are not efficient anymore, and we can correct this by the method of weighted least square. We looked at these two tests, Breusch-Godfrey test and White test, for how to detect for the heteroscedasticity. So these all we discussed last week. So today I would like to look at autocorrelation and model specification. Before we start next week with the first topic in the cumulative time series, this part in the module. So let's look at the first topic today I would like to cover today, which is autocorrelation. So we need to learn about the sources of autocorrelation, how to detect for autocorrelation, and how to correct or how to remedy for autocorrelation if it exists. So the basic idea here is that the classical linear regression model assumes that the covariance between UI and UJ should be 0. And that means the disturbance term relating to any observation should not be influenced by the disturbance term relating to another observation. This is and if we want to interpret this with time series data, so if we assume we have a labor strike happening this quarter, the disturbance or the effect on output should not be carried over to the next quarter. That means there is no autocorrelation. Okay, so if we think in terms of cross-section data, so that means the effect of an increase in of a family's income, one family's incomes on its consumption should not or is not expected to affect consumption expenditure of another family. That is the case if we don't have autocorrelation. But this is not the case. So the case would be if there is a strike this quarter, it is more likely to affect output in the next quarter too. And that is what it means. So when the covariance between UI, UJ isn't 0, is not equal to 0. So there's some kind of impact here that coming from because of the labor strike. This quarter will be carried over to the next quarter. If we think about this in terms of cross-section data, so again, so if the consumption expenditure of one family increases because they have an increase in their income, this is likely to affect the other families as well. Again, if that is the case, that means we have autocorrelation. But if you see this is very easy to understand here with time series data, and that's why autocorrelation is a prominent formula of with time series data. So it is likely to be the case with time series data more than cross-section data, because there's a possible correlation between a shock in time t with a shock in time t plus 1. So think of this as the labor strike this quarter and how likely this will affect the output of the next quarter, and so on. So this is something that happens more likely or more often with time series data. So there are different reasons, different sources where autocorrelation happens or where autocorrelation comes from. So most time series variables like GDP, price indices, production, employment, unemployment, they exhibit business cycles. So this is something very prominent with, it is something built on in these macroeconomic data, and that means it continues until something happened, like something changed, like interest rate or tax or both, and then this would slow them down. So there's kind of built-in feature in time series data that causes autocorrelation. Another reason why we would have autocorrelation in a model is the excluded variables. If you exclude an important variable, and this variable is autocorrelated itself over time, because the influence of this variable, since you exclude that variable, it goes into the, or it is captured by the error term, and that's what makes the error term correlated over time. So, and that is so it's absorbed by UI, and that's why you will see autocorrelation. Another reason is incorrect functional form. So let's say you should have used a log form, but you actually used a linear form. So again, this is something we look at today when we look at the specification errors. So this is another reason. So the cobweb phenomena, for example, if the supply of agriculture commodities react to price with a lag, which means if, let's say, the price change this year, then as a producer you will react to this in the coming year, so not in the same year. Okay, so it's very difficult to do in the same year, so it comes with kind of a lag. So all these are sources, are reasons why we could see autocorrelation. Again, data manipulation or smoothing. Sometimes when you interpolate or extrapolate your data, then again this will result in autocorrelation. Or sometimes by averaging or smoothing, this again could be another source of autocorrelation. So these are different sources of autocorrelation. So they happen, as we said, it's likely to happen with time series data, not cross-sectional data. So the question now, what are the consequences of autocorrelation? What would happen to all this estimation if we have autocorrelation? So if autocorrelation exists, we basically will have all these estimators still unbiased and consistent, so this is not the problem. If you have a large sample, so it's still normally distributed, but the problem here, they are not efficient. They're no longer efficient. That means they are no longer blue. They are no longer the best. Okay? So also in most cases, this will affect the standard errors. They will be underestimated. And since they are not reliable, then basically, because they are, most times they are underestimated, they are not reliable. So you can't use them for statistical inference. So these are the consequences. This is something happened because of autocorrelation. So autocorrelation is a problem, and we would like to address. So how would we know we have autocorrelation then? So now we understand what is autocorrelation, why would it happen, and what are the consequences for OLS estimation when it happened. Then the question here, how to detect for autocorrelation, how to test for autocorrelation. You could do this by the graphical representation of the values of the residuals. So you can plot your residuals, and then you could look for like a kind of systematic pattern in your residuals. And if such systematic pattern exists, that means you have there's a problem of autocorrelation. So I'll show you some examples. If you plot your residuals, and this is something that you've seen, so it's kind of cyclical pattern, that means we have the problem of autocorrelation. If you plot the residuals and you have kind of upward linear trend, again, this is a reason to suspect that you have autocorrelation. This is another example. So this is a downward linear trend again. So just notice these are the residuals against time. So this will give you some hint whether you have autocorrelation or not. So all of the examples I showed you so far, that they mean that you should suspect the presence of autocorrelation. This is again a quadratic trend. So whenever you see a trend, you need to see a systematic pattern in your residuals. When you plot them against time, then you should suspect the presence of autocorrelation. But if you get something similar to this, there's no systematic pattern, so that means that it could be a sign of not having the problem of autocorrelation, because we have no systematic pattern when we would plot the residuals against time. So this is how to detect for autocorrelation graphically or informally without implementing a formal test. But you still can test for autocorrelation. So to see that, we will look at first an example. The data are now in Blackboard, so you can download this data. So if you go under the folder data set, so you'll see table 6.1, and this is time series data from 1947 to 2000. This is US data. So the variables you'll see in this data set: real consumption expenditure, real disposable personal income, real wealth, and real interest rate. So if we want to estimate the consumption function, so consumption here, real consumption expenditure will be the dependent variable, and this will be the right-hand side variables or the independent variables. So this is what we did now. So this is the consumption. Here are the other three variables, the independent variables. So first of all, before jumping to looking at formal test of detecting of autocorrelation, so if we want to look at the graphical representation of this to see whether we have a problem of autocorrelation or not, you will see that the residuals, so for example, I plot here the residuals against the residual in time t-1. This will show you that there's some kind of upward trend or some kind of positive autocorrelation. Is it clear why this is the case? Yeah? Okay. So that's the main idea here. So if when you plot the residuals, you see if you see any kind of a pattern, then that means you probably have the problem of autocorrelation. So what I'm going to do now, I'm going to look at the formal test. One of the tests that we could use for detecting for autocorrelation is Durbin-Watson test. So before we jump to what the test does, we need first to be aware of the assumptions that this test makes first. So first, the regression model includes an intercept term, so you should have the beta node in your regression. The regressors are fixed in repeated sampling. This is part of the classical linear regression model assumptions already, so we have this one. The error term is normally distributed. The regressors do not include the lagged values of the dependent variable yt, so you shouldn't have yt minus 1 on the right-hand side of your model. So just remember, these are the assumptions related to the Durbin-Watson test. So the second, we continue with the assumptions. So the error term should follow the first order autoregressive scheme, which means that the error term in time t, it depends on the error term on time t minus 1, so it doesn't go back further than one time period, plus some random error vt. So rho here is the coefficient of autocorrelation, which takes the value between -1 and 1. So again, these all are the assumptions of Durbin-Watson test for autocorrelation. And to make a decision, the Durbin-Watson provide two critical values of the D statistic. So once you have the D statistic from the Durbin-Watson test, then you've got D lower. When you look at the table, you've got D lower and D upper. And the value, or D value, always lies between 0 and 4. So if it's closer to 0, then that should give us an indication that we have positive correlation. If it's closer to 4, that means we have negative autocorrelation. But if it is close to 2, then there is no evidence of autocorrelation, of first order autocorrelation. Why am I saying first order autocorrelation?
Second order.
Because this is one of the assumptions that we made about the Durbin-Watson test. So it look only at AR1. And this is one of the drawbacks then of Durbin-Watson test. So we actually assume the error term or the autocorrelation is the first order scheme, which means that the error term in time t depends on the error term on time t minus 1 only. So there's no, it doesn't go back further.
So you just do the same test again, but with ut minus 2.
Well, the idea here, this is why we would like to look at this is the same what I just said now about how to make a decision with the Durbin-Watson. That's why we could look at the Breusch-Godfrey LM test, which doesn't restrict us to the case where we have the error term depending on only the first leg. Okay, so again, just before I jump to this point, so again, this is very. Let's show you how the decision is made in Durbin-Watson test. So if the value very close to 4, that means we have evidence of negative autocorrelation. If it is very close to 0, that means evidence of positive autocorrelation. If it is close to 2, that means there is no autocorrelation. And these two zones here, these are indecisions, which means we can't make a decision if the D statistic falls either here or here. So that means we can't make a decision. But if it falls here, so which means it's very close to 2, that means there's no autocorrelation. Again, if it is very close to 0, that's an evidence or an indication that we have positive autocorrelation. If it is very close to 4, that's an evidence. This is evidence of negative autocorrelation. And going back to your point, yes, so that's why we use the Breusch-Godfrey LM test. So this allows for lagged values of the dependent variables. This is restricted in under Durbin-Watson test, so we don't have this in the Durbin-Watson test. So you could include yt minus 1, so the lag dependent variable should be among, or can be among the regressors with LM test. You can also use higher order autoregressive schemes such as AR2, 3, etc. So you could include U, T minus 1, T minus 2, T minus 3, and so on. So this is the general form as you see. So we have UT, the error term in time T, depends on the error term in T minus 1, the error term in T minus 2, etc. up to the error term in T minus B. So the null hypothesis of this test that there is no serial correlation, meaning that these rows here, row 1 equal row 2 equal up to row P, and they all equal 0. So if you accept this, so if you can't reject this, that means there is no serial correlation. But if you reject it, then there's serial autocorrelation. Okay. So I used the same data that, by the way, I didn't show you this with the Durbin-Watson because already EViews produce Durbin-Watson statistics right away when you do the regression. So you already have them here. With the, if you want to do the LM test, then you need to do this in EViews. So you need to do it yourself. Then this is the output for the same regression we had. So what you need to look at here is the F statistic. Then again, the p-value is small. Then you reject the null hypothesis. What is the null hypothesis? There's no serial correlation. So if you reject that null hypothesis, that means there's serial correlation, there's autocorrelation. So that means in this example, in this regression, there's a problem of serial or autocorrelation. So again, what we looked at now, we discussed what it means and what are the sources, what are the implications, and then how to detect for autocorrelation. So now we have the problem with autocorrelation. So what we should look at next is that how to correct this, how to fix this. So how to remedy for autocorrelation? We could use the first difference transformation, assuming that the error term follows this AR1. So if autocorrelation is AR1, meaning that the error term in time t depends on the error term in time t minus 1, so it goes back one lag. Then if you take the first difference, this will sort out the issue of autocorrelation. And that means you would take the first difference of the dependent variable and all the regressors. So if of y on the left-hand side and all the regressors on the right-hand side. And this is an example of how would you do that. So this is the first difference of the consumption expenditure. And this is the first difference in all of the other regressors, all of the independent variables. So if you compare this with the first estimation in level without taking the first difference, you will see that the Durbin-Watson statistic is 1.2, so it's very low. So when you compare this to the one with the first difference, here you'll see that the Durbin-Watson is becoming more closer to 2, where we said if it is very close to 2, then we can conclude that there is no autocorrelation. So you see how it's happened now. So if you take the first difference, it could help to get rid of autocorrelation. There are different ways, other ways that you could deal with autocorrelation. So you could do what is called generalized transformation. So you estimate the value of rho. Rho here is this is the rho. So you could estimate this rho, and then you use this to transform the whole model, and that should help to get rid of autocorrelation. So first you estimate the value of rho through the regression of residual and lagged residual, and then, which I just showed you now, and then you use this value to run the transformed regression. Another way, which is the newest method, and this is very easy in EViews to obtain, I think. So you can generate what's called hack standard errors, which is heteroscedasticity and autocorrelation and consistency. So you correct for both together in any views. Okay, so that's all now for autocorrelation. So any questions? Anything that's not clear about autocorrelation? What we mean by autocorrelation? What are the sources of autocorrelation? What are the consequences of autocorrelation for OLS estimation, and then how to detect for autocorrelation using graph, and formally using test Durbin-Watson or Breusch-Godfrey LM test. Okay, and then how you would correct for it using first difference or any other method. Okay, so that's everything we covered on related to autocorrelation. So any questions? Is it clear? Okay, so next week in the seminar, we'll take more examples about this and how to do this in eViews. But now let's move to the next topic for this lecture, which is specification errors. So specification errors could be one of these. If you have underfitted model or overfitted model, or if you have an incorrect functional form, or if you have measurement errors. So these are different types of specification errors. So underfitted models, when you omit or exclude important variables, so you don't include them in the model, then the impact or the influence of these goes to the is captured by the error term, and that is the first case. And we'll see how to deal with this now. The overfitted models means that when you include irrelevant variables that are not important to the dependent variables, so they should not be in the model, and we'll see what are the consequences now. Of course, incorrect functional form, when you use the wrong functional form. So use, for example, a linear function where you should have used a log form, for example. Measurement errors, we'll see what is the problem if we have measurement error in the dependent variable or in the one of the independent variables. Okay, so let's start with the first one. So again, it's very clear that the classical linear regression model, something we covered before, assume that the model is correctly specified. So, but what do we mean by correctly specified? There is no such thing as perfect model. So you always have you could be looking, or you should be looking at the best model, but again, it is very difficult to say this is a perfect model. So most models will be far away from being perfect, because we don't have any way to judge which one is the perfect model. So we're far away from this, having a perfect model, but in general, there are like general guidelines where whether your model that should tell you whether your model is good or not, is good enough or not. So an econometric model should capture the main features of an economic phenomenon. What does that mean? It should take into account the underlying economic theory. So if I'm looking at modeling consumption function, for example, consumption, then economic theory tells me that consumption depends on income. So this any econometric model that you would have should include income on the right-hand side. So that's based on economic theory. Again, it should also take into account any prior empirical work, and that's why we say it is very important to look at the literature to see what people have done before, and that would help you which variable you should include in the model, and intuition as well. So there are different factors that you should keep in mind when you build an econometric model that capture any economic phenomena. So you should keep all this in your model. So, but there's no model that can take into account every single factor that affect a particular object of research. That's why, because you can't include all variables, then you should include important variable. That's why we wouldn't have a perfect model, but we're trying to be close as possible to that perfect model, to that best model. Okay, so again, a correctly specified model doesn't exclude any core variables, so any important variables. That the example I gave about the consumption function, if economic theory tells us that income is important when modeling consumption, then income should be on the right-hand side, should be one of the independent variables that you would include in your model. Also, it shouldn't include any trivial or any small, like any variables that doesn't have really much impact on, or big impact on the, or doesn't help much in explaining the dependent variable. So you could actually ignore these. Again, it should have the suitable functional form, and that's something that we look at now. And there should be no measurement errors either in the dependent or the independent variable. So again, these different things you keep in mind if you would like to get a correctly specified model. So you should take into account any outlier you may have in the data. You should be aware of the probability distribution of the error term, and you should include a non-stochastic regressor, and there should be no simultaneous bias, which basically related to a single equation model when you have only one equation. So, okay, so let's look at the first type of specification errors, which is the underfitted model, which means when you omit important variables. Okay, so there are important variables that you should have included, but you haven't, and the impact of these is captured by the error term. So what's happened here? So let's look at an example. Again, this data is now available on Blackboard. So if you want to replicate the results, or if you want to play with this data to find a better model or a good model, then you could actually, I would encourage you to do so. So this data to model hourly wage determinants. So we want to see the main determinants of hourly wage. What kind of factors that could determine your hourly wage. And this data from 1995 in the US, and include 1,289 workers. So this is the first regression I ran. So we have wage as the dependent variable. So this is the hourly wage rate. And on the right-hand side, we have a dummy variable that tells us whether the object or that person is a female or male. So this is dummy variable. Non-white, dummy variable for non-white. Another dummy variable for whether they are part of any union. And education, here's the number of years of education. Experience is the number of years they've been or they have in this job. So the first thing we'd look at here, okay, so all variables or all these are significant, statistically significant, but what about other factors that could determine the hourly wage rate? So based on theory and empirical work, some researchers would suggest that we should include the experience raised to the second power to determine the rate at which this will increase. So basically what we learn from this model is as your experience increase, then you should expect that your hourly wage rate would increase too. So there's kind of positive relation. But if you want to capture the rate at which this would increase as a result of increasing your experience, then you should include the square term of experience. So again, if you look at this, it is highly significant. So the question here, which one is better model? Is this model? So is experience important for this model, or we shouldn't include experience square, sorry, or we should just stick to the first model? Another way, or another thing that we could look at, or another specification, or another important variable is whether that you could be an experienced person, or we could look at whether two people with the same experience, whether their hourly wage will be different based on their gender. So we could have some interaction term between experience and the female dummy. So again, this is a third specification where, so we include a third variable here. So the only difference here, so each time I'm just introducing a new variable. So this is the basic regression, the basic model. Then I added the square term of experience. Then in this one, I added the interaction term between experience and female, and notice that it's also statistically significant. So the important question that we should have now, we should ask ourselves, which one of these models is the best or is better at explaining the hourly wage rate? So this is something we need. How would we do that? So if these two variables are important and we drop them, then there will be a problem, because the impact or the effect of these two variables on hourly wage will go into the error term, and this will cause a specification bias. So one of the tests that we could run is the Ramsey RESET test, where from the incorrectly estimated model, you obtain the estimated or fitted values of the dependent variables. So let's assume that the first model, that was the incorrectly estimated model, okay? So what we need to obtain, what we need to get is the fitted values from the first one, and then we estimate the original model, including these on the right-hand side. So we include y hat on the right-hand side as one of the regressors, and then the first one, the first model, we call the restricted model. And then the second one, in which we included the fitted values of the dependent variable on the right-hand side, we'll call it the unrestricted model. Okay, so we've got two models. The restricted one, which is the first one, the one that we think it's incorrectly specified, and then the second one, which is the unrestricted one, where we included the fitted values of y as one of the regressors. Then the null hypothesis that the restricted value, the restricted model, which is the original model, is correct, then we can use F-test to decide whether to reject or to not reject this hypothesis. So if the F-test from this show that it is statistically significant, then we can reject the null hypothesis, meaning that the restricted model is not appropriate at the present situation, meaning that if the one that we didn't include, or the basic one that we had, this one, would be incorrect, okay? Because there are important variables that we didn't include in the model. So let's look at this, how to do this. So this is the basic one. So this is the restricted model. You see, we've got these variables: female, non-white, union, education, experience. Then we didn't include the other variables that we think are important too. So we didn't include the square term of experience. We didn't include female, the interaction term between experience and female. So, and we want to check whether, we want to test whether this is an appropriate model or not. So again, so how would we do that? So we need to get the fitted values, which means the wedge hat, so the fitted values from these, and include this in another regression where we run the regression again, but we will include the fitted values of the dependent variable in the right-hand side, and then we do the F-test. So this is the output from e-views of this Ramsey RESET test. So what we want to look at is the F statistic here, and given that it has a very small small p-value, then we reject the null hypothesis. What is the null hypothesis again? So what that means, if we reject the null hypothesis, that means that the model, the restricted model, is not appropriate. This is not the best model we can have. Okay? So that means we need to add more variables. So this is one way to do this. So if you look at how the test does this, so look at here, what is wage? So let's compare these two. So, sorry, this one. So we have wage here. Remember, these are the regressors here. So this is the one that we discussed in the beginning. And then what the test does is the same regression. So wage here is the dependent variable. The same regressors here, but it adds the fitted values of the dependent variable. These are the raised to the second power and the third power. Okay. So and then this is the test output here. This is the or based on this F statistic, you can make decision whether to conclude that the restricted model is appropriate or not, and given that we rejected the null hypothesis, then that means the restricted model is not appropriate, okay? So there are two drawbacks to this. Firstly, if the model found incorrectly specified, like the case we have now, then the test doesn't give us any alternatives. So what we should do then, we don't know. And also doesn't offer any guidance about the number of powered terms that we should include. So for example, here I choose to put 2. You could have put only 1, 3. So you don't know really how many terms you should include here. So the test doesn't help you to do that. So it doesn't.
In that example, hardly anything is.
Yeah, but this is not what we're looking at. So we look at the F-test. So we're not really looking at the. We're not really interested in the whether these are significant or not. I'm just saying this is the mechanism. This is how the tests work. So this is the output. This is where you can make conclusions. So these are by these two slides. And if you get these two results together, I split them between 2 slides because it wouldn't be easy to see in one slide if you have both. Secondly, because this is the important part, this is where you can make, where you need to look at to make a decision, okay? And then this just explains to you the mechanism, how does it work? So the procedure itself, how does the test, what does the test do? So basically, get the fitted values from the previous regression, from the restricted one, and add them to the right-hand side, and then use F-test to get this one. Okay? So basically, based on that, then we reject the null hypothesis, meaning that the restricted model is not appropriate. Okay? So again, so what is the appropriate model? It doesn't tell you, so we don't know. Okay? So that's the conclusion, the only conclusion we can make in this situation. That's why there's another test you could look at as well, which is the Lagrange multiplier LM test. So another way to do it. So again, remember we trying to see whether we have omitted some important variables, and so one way to do this is to do this test, Ramsey RESET test, or you could do the Lagrange multiplier LM test. So from the original model, the first one we estimated, then you get the residuals. So if the model is correct, we expect that the residual should not be related to the regressors omitted from the model. So let's say experience squared. These are omitted from the basic model, the first restricted one, or female, the interaction term between experience and female. So we expect that this one, the residuals coming from the restricted model, should not be correlated with any of these omitted regressors. Okay, so what would we do then? Then we run another regression where we have the residuals on the left-hand side, and then we include the same regressors plus the omitted regressors that we think they are important, which in our case are experience squared and the interaction term between female and experience. Okay, so this is an auxiliary regression. And then we use R squared from that regression, from the auxiliary regression, times N, and then based on that we can make a decision. This would follow chi-square distribution, and the degrees of freedom equal to the number of regressors omitted from the original regression, which means in our case 2 regressors. So we omitted experience squared and the interaction term between experience and female. So the important thing now is how to make a decision. So we reject the original or restricted regression if the computed value is greater than the critical value. That means the original model is not well specified or is not correctly specified. So how to do this? Again, this is the restricted model. Okay, so we have wage regressed on these variables. So we think that experience squared is important, and the interaction between female and experience is important too. So basically, so that means this omit 2 variables, this basic regression or restricted model omitted 2 variables. So what should we do now to do the LM test here? So what we need to do is to get the residuals from this regression, and then run an auxiliary test, so where you have the residual on the left-hand side, And on the right-hand side, you will say you have exactly the same regressors, plus the ones that you think they are important, or the ones that you omitted from this regression, which are the experience squared and the interaction between experience and female. So again, so let's see what we've done here. So E1 here is the residuals from the previous regression, from the restricted model, and then we have exactly the same regressors plus the ones that we think we omitted from the first one. So we have experience squared and experience times fair, or the interaction between experience and female. So what we need to do, what we need from this regression, then we need to calculate NR squared. Remember, this is the LM. So N is the number of observations. So if you go back to check the number of observations, so it's 1,289 times R squared from this regression. Okay? This will give us 32.35. So this would follow chi-square. So you need to compare this with in the table. You go to chi-square distribution, where the degrees of freedom is 2. 2 here. Why is it 2? Because we omitted 2 variables. That's why it's 2. Okay? So if you include here 3 variables, then it will be 3, and so on. So it's the number of omitted variables. And then you compare both. So if you go to a chi-square distribution at 5% level and 2 degrees of freedom, you will see this is the critical value. So the computed value, the tested statistic, is much greater than the critical value. That means we reject the original model, or that include that, or that indicate that the original model, which is the restricted model, this one, is not correctly specified. Meaning that it is important to include experience square and the interaction between experience and female into your model. So this is another way to test for underfitted models, or whether you have excluded or omitted some important variables that they should have been in your model. Okay? Any question? So that's the first type of a specification error. Just again to look at what we did. So the second topic we looked at today is specification errors. And we said with the specification errors, there are different types of specification errors. The first one is the underfitted models, where you excluded or where you omitted important variables. Okay?
How I can find what the variable I should try?
Yes, that's literature review. That's the economic theory. That's what we explained. Yeah, that's in the first lecture. That's what we discussed in the first lecture. That's why I was keen to show you where econometrics come. So econometrics comes after you've done your basic work, like as a researcher. You have a very clear research question. You looked at the literature. You know what people done before. Then so you start where the literature is. Then you build on that literature. So you understand the theoretical background of the phenomena you're trying to model. Then that will tell you. You look at the empirical work, the previous work. Then it show you what variables you should include in your model. So all this should give you an idea about what sort of variables should be on your model. Okay. Plus, if you suggest any like a new variable, for example, then you should provide some kind of theoretical explanation. Why do you believe that this variable is important in explaining the behavior of your dependent variable? Okay. So that's a good question. So it's very important to be aware of, as I said, any theory or empirical work that was done before in your on this phenomenon, and then that will give you a good idea of where to start, what type of variables you should include on the right-hand side. Okay, and also will give you an idea about how these variables are measured, where the data come from, if there's any limitation, what kind of econometrics or econometric methods were used in the past, and what are the limitations, etc. So this is very important to do before jumping into the data and econometrics and do econometrics. Okay. So let's move then to the next point. Then the overfitted models. Overfitted models, as we said. So the previous case where We discussed this case when we have variables, important variables that we omitted, and the impact of these would be captured by the error term. So in this case, we have overfitted models, meaning that there are irrelevant variables, unimportant variables, that you, by mistake, you just introduced in the model. So you included them on the right-hand side. So sometimes you do this thinking that this would help increasing or improving the R-square, as you believe that this would may provide a better model, or for any other reason. So it doesn't really, or maybe you didn't know they are not relevant. So whatever the reason was, so this is not the what we are interested in here. But at the end of the day, we understand that there are some consequences when you have overfitted and overfitted model, meaning when you include variables that are not relevant to the model. So we will continue with the same example. So the same example where we're trying to model the hourly wage rate. We have the same model we started with. And for example here, what I tried to do, I tried to add age in this model. So on the right-hand side, I thought, well, age is important. Okay, if you go back to the lecture we did last week when we discussed perfect multicollinearity, this is some kind of specification error because age is highly correlated with experience. Okay, and as I told you, if you remember, most software, statistical software today, if you have perfect multicollinearity, it will give you kind of error message, and that's what happened here with if use. So I tried to include age, and that's what if use gave me. So give me regressors may be perfectly linear. So it warns you. So there's no. So but let's say if we introduce a variable that is not important but is not perfectly linear, the software will give you the results, but you will not be aware of this. But if you suspect that there is any one of the variables that, or one or two variables, may not be relevant to your model, then you could do the F-test we discussed in the first lecture, the exclusion restriction test, which we discussed in the first lecture. Okay, so this is another way to go with this. This is just an example to show you how age, how experience depends on age. It's very highly significant, statistically significant. R-square is very high, so it's really this kind of positive correlation between experience and age. It's something you would expect. You should expect, by the way. Yeah. So that is that's with the overfitted model. So I didn't show you how to test for having an overfitted model because we already covered this in the first lecture. The example about, I think, was wealth. Whether was it important to include one or two variables, if I remember. And the idea is that you could use F-test to test whether you should include any number of variables, let's say 2 or 3 variables, you have some suspicion, you're not really sure about whether they should be included in your model or not, then you can run F-test the same way we showed in the first lecture to test whether you have an overfitted model, meaning that these 2 variables aren't important for your model, you should exclude them or not. That should be done by, or that could be done by the F-test that we showed in the first lecture. Okay, so again, let's go back to the types of specification errors we're looking at today. So the first one, the underfitted model. Overfitted model is the second one. So an underfitted model when you omit some important variables. Overfitted model meaning that you include irrelevant variables. The third type, which is the incorrect functional form. Incorrect functional form meaning, for example, you use a linear form where you should have used a log function or whatever, a different functional form. So we follow the same example. We show that, okay, we compare between the linear with the log linear for the wage determination. So we'll start with the linear form. We're already familiar with the results, so this is the same results. So, but now we include all the variables that we think are important to in explaining the hourly wage. But as you can see, this is linear. These are linear variables. Then again, sorry, this is the wage is linear, so we don't have log or any kind of functional form here. But we compare this with the log len, where we have this variable here is in the log form. Okay. So which one is better? Which one we should follow? Is it the log len or the linear form? So that's another question. That is related to the functional form. So again, that could be one of the specification errors. So if the linear function was the best one, and then you use the log len or the log function, then that's another error, or the other way. So it could be the other way, where you should have used log, but you haven't, and used the linear form, and that is again, that could result in specification error. Okay, so how would we test that? How would we know which one is better? Is it the linear form, this one, or this one? So it's very difficult just by looking at the coefficient, because they're all significant in both cases. So it's significant here. You see, they are all of them mostly significant here, and the same thing here. They all are statistically significant. So one way to do this, there's a very simple procedure that you can follow. So basically, you could have this is how to generate a new variable in eViews. So what I'm trying to do here is to get the wage average. So get the average. So that new variable will be equal at mean between bracket wages. That will give you the wage average. And then you create a new variable, which is the wage divided by the average. And then we run a new regression using both forms, the linear form and the log linear form. Okay? And what we need to do is we need to obtain from this new regression the residual sum square. And I will tell you how to use that from both models. Again, so this is a very simple transformation in the model. So what I did here is I created a new variable that, whatever you can name it, whatever you want, but this is the mean, the average of the wage. And then you divide wage by the average, so you divide each observation by the average, and then you run a new regression using the two forms that you're not sure about. You want to compare, or you want to know which one is better. Okay, so you have the linear and the log linear. This is in our example. We're trying to compare between both. And what you need to do is to obtain the residual sum squares of these two. And then I will show you the formula that you need to use, and based on which you will decide which one is the best. So this is the new regression. So wage new, I just called it wage new because that's how I named it here. That's what I named it here. So you can name it anything, but basically this is wage divided by the average of wage. So this is the linear form, so there's no log here, okay? And then again, what we need to do here, what we need to obtain from here is the sum squared residual, remember? That's what we need to obtain from here. Again, going back to what I said here, so you need RSS from both regression. So I run the first one in the linear form, and you need to get this value, and then you run with the log here. So this is the log of wage, and we obtain the sum squared residual, and this is the formula you need to use. So to calculate lambda, here is n divided by 2. This is the log of this is the residual sum square from the first one to the second, and divided by the second one, and this would follow chi-square distribution with degrees of freedom 1 and alpha. And just remember, the larger one should be on here on the numerator. Okay, so it depends. So it doesn't matter which one you run first. Just put the larger one at the top, and then this is the statistic, or this is the value or the computed lambda. And what we need to do is to compare this with the critical value. And basically, this is a very large one. So meaning that you will reject the null anyway, or you will. In all cases, it will be. I didn't look at the table because this is very large value. So basically, it's greater than the critical value, which means if that is the case, then the model with the lower RSS is better. So which one here is with the RSS is better? So it's 272 277, which is this one. So that means this one, this functional form is better than this one in explaining the behavior of this variable, the dependent variable, the hourly wage rate. Again, so this is very basic, very simple procedure to compare between two different function forms. And that was one way to decide which one you may or you should be doing. But that, by the way, you could also, if you just plot the dependent variable and you compare between the log, the wage without the log, and then with the log, you will see that log wage is more, it's much closer to a normal distribution than the wage. So if you plot the dependent variable, also can help you to give you some idea about how it looks like. Is it a log? Should you use the log wage or should you use just wage? Okay. But in this case, if you use the same data, I encourage you to do that. Just plot wage first, and then plot log wage, and see which one is better, or which one would be closer to be normally distributed. So it would be log wage. Okay. So this is again another way. But even without knowing that, even without plotting that, this is another simple procedure that you can use to see which functional form that might be better explaining the dependent variable. Okay? So we'll compare it between linear and non-linear, then you can play with the data. And again, as I said, one way to do that, just plot the dependent variable and see how it looks like. Okay, any question? So these are, again, we're talking about specification errors. What we covered, underfitted models, overfitted models, and the incorrect functional form. The last one, which is very straightforward, which it's not going to take long, the errors of measurement in the variable. So if this happened with the regression, which means with the dependent variable, then the old estimators are still unbiased. Okay, so it is less problematic, but that is the bottom line here. So if the problem happened with the dependent variable, it is less problematic. The OLS estimators are still unbiased. The variance and standard errors of OLS estimators are still unbiased, but the estimated variance or the standard error are larger than in the absence of such errors. But in short, like to just conclude the whole thing, errors of measurement in the regression or in the dependent variable don't really pose a very serious threat to all estimations. But the bottom line here is that these are not, the OLS estimator are not affected by this. So they're still unbiased. The only problem, as I said, is with the estimated variances. They are larger than in the absence of the error, but they are not very serious threat to the estimation, to the OLS estimation. But the problem becomes very serious when the error, the measurement error, happened in the one of the variables on the right-hand side, the regressors. Okay, so OLS estimators become biased and inconsistent, and these are two problems. Also the errors in a single regressor, so if this measurement error happened with one regressor, with one X, this is likely to affect other coefficients as well, the coefficients of other variables as well. So it's likely that it will affect the coefficients of the other regressors in the model, and it's not very easy to establish the size of the direction of bias so you can correct for. But the way to do this, the way to deal with this, is to use instrumental variable, proxy variable, and this is something we will cover in week 8. Okay, so we'll learn more about instrumental variables and how to use instrumental variables. Okay, so again, this is to deal with the errors of measurement in the regression. So as I said, with the regression might be not a very serious problem, but any measurement errors with the X's or with the regressors, that will cause a serious problem, and that's why we should use instrumental variables in this case, or we should use a proxy. Okay, so that's all. That's everything I wanted to cover today. So just to sum up what we covered, we covered autocorrelation, what it means, and what are the sources of autocorrelation, what are the implications for all this estimation, and then how to detect, how to test for autocorrelation, and then how to deal with the problem if it exists. Again, we looked at the second topic, we looked at specification errors. In particular, we looked at omitted variable problem or bias, which we call the underfitted model, or overfitted models when we have included a relevant variable, and we show you how, in the first case, we show you how to test for it. In the second case with the overfitted model, I told you that you could do F test, the same way we explained in lecture 1, in week 1. And then the third type of specification errors we looked at is incorrect function form, okay? And again, we looked at an example between linear model and log linear model, and we showed like a very simple procedure how to do that, and then we finished by looking at the measurement errors, whether it's in the regressor or in the regressor. Okay? Any questions?